Martin Voralik is a Czech scientist. He works in Myria in France as senior researcher, and he's the head of the team Serena, and he also holds a professor degree at the Charles University in Prague. Previously, he was an associate professor at the Sorbonne University in Paris, France, and he serves as an editor of Computational Geosciences, Application of Mathematics, and Acta Politecnica journals. He held the RC Consolidator Grant, GATIPOR, in 2015-2021. His research interests include partial differential equations, numerical analysis, and scientific computing, with a specific interest in a posteriori error control and adaptivity, and he works mainly on application to flows and transport in porous media. So his talk is on adaptive regularization and linearization for Nonsmooth and Degenerate problems. You can raise questions, possibly using the Q&A, and at the end, Martin would be pleased to answer you.
So, hello everyone. Thank you very much, Luca, for a very kind introduction, for all of the person who take care of running the seminar, for invitation. It's a great pleasure and honor. I hope you can see my screen. Is it fine?
Yes, yes, perfect.
Okay, so that should be good. Yeah, so I would like to show you some of our recent results that I obtained in collaboration with a selection of colleagues. So they are colleagues from Paris, France, working at the IFB New Energies, the former French Petrol Institute. It's Ibtial Ben Garbia, Joël Ferdi, and Suleiman Youssef. There were people connected to INRIA Paris, Ari, who did his PhD here, Condi, who did his postdoc, and I appreciate collaboration with our industry colleague, François Ferrot from Triskel Innovation. Yeah, you've already introduced the title, and actually I would like maybe now jump directly into the introduction, and my introduction is essentially trying to explain you the keywords that you see in the title. So let me try to explain the 4 words you've seen in the title. So first of them was non-smooth. In laws that we see describing flows in porous media, very often we have functions as the one that is plotted there, function, real function, real variable. I give you pressure, you give me the saturation, pressure saturation functions, which can be such that there is no derivative. So that's what I more broadly call a non-smooth function. This very precise one is the Brooks-Corey one describing the pressure saturation relationship. And they're functions that I call degenerate in, again, rather broad sense. It means that they are functions who take or approach the value actually as a function value or derivative 0, or actually the same problematic for derivative plus infinity. Again, very precise example, the saturation relative permeability Brooks-Corey function, which has this property. Now, 2 claims about these kind of state functions, real-to-real functions. In my feeling, they are really omnipresent in laws that describe flow in transport and porous media, point 1. And point 2, yeah, these are very often at the heart of troubles of convergence of standard iterative linearization schemes, like, for instance, the Newton method. Well, there's a plethora of recipes how to fight with this. One of the most easiest to put in place, probably also most heavily used, just for time evolution problems, you reduce the size of your time step, you do time step cutting. That kind of makes the problem less stiff, and maybe your initial linearization scheme will converge. But yeah, there are many other ways how to try to fight damping. You switch the scheme from 2nd order Newton to some 1st order, like fixed point, Picard, L or M. yeah, I will also be covering things that touch variational inequalities. So there, the whole branch of methods goes to semismooth approaches or pathfinding. Yeah, you can do variable switching and many other things. Well, in my talk, the last two keywords were regularization and linearization. And this is very much what is our idea, our approach, our suggestion, our methodology. Adaptive regularization is nothing but taking the type of non-smooth and degenerate functions I've just shown, like the one here still given by the black curve, and approach it by a sequence of nice behaving smooth functions that have derivatives, potentially many derivatives, that are in the eyeball measure already nice. So you've got the black curve here that has this tip here, no derivative present in this point. And we have a little sequence of functions starting from some, rather high regularization parameter epsilon value, like the green one, which is, as I said already, in the eyeball measure, a rather nice one. And then as I go down with my regularization parameter, I approach the original physical law function. So that would be the example for the non-smooth one, the Brooks-Curry pressure saturation. And the other example I had was Brooks-Curry relative permeability function, which initially touched here 0. And there I just simply, push the function up by the value of this parameter epsilon. So, of course, this is a very, very common, known, old approach, how to fight problems. Well, where we wanted or did take it in the direction that I believe is novel and also working in practice. We hope so. Well, we have this sequence. We've got this regularization parameter, and we make this adaptive approach where I start maybe from a bigger epsilon, like this green curve here. Well, I obtain a rather nice function replacing the original bad ones. I do just a few steps of my favorite linearization scheme, say Newton one. Well, the nonlinearity is rather gentle. I may have a good initial guess, so hopefully I will converge in a few steps. And then I just decrease my epsilon. So I move from the green curve to the red one here, and reiterate, I go back to the point 2. Well, the details are then really in how precisely do I do this? How do I steer such an approach? And then, well, the work adaptivity is for me always connected with estimating how big is the error that I'm committing. I speak here about error components. I will have 2 error components. The one we've been just discussing is the regularization, which is essentially how far is first this green curve from the black one and then the red one from the black one in some appropriate way of measuring things. And the adaptivity, the heart of the procedure, the steering, is that, well, I don't really bring this epsilon to 0. I just make it small enough such that the committed error in regularization is sufficiently below 1 that will always be there. The error component, which is always present in any numerical simulation, is the discretization error. So this is our adaptivity on regularization. And intrinsic is this one here. I said I do a few steps of Newton. Well, what does it mean in practice? Few steps. Then this will be covered by this second item here. I have also an a posteriori error estimate for the component of the error associated with linearization. And I make this component just a little below the one that already is there. It's regularization. So it's some kind of cascade. Linearization is below regularization, and regularization is below discretization. So that would be essentially the title, adaptive regularization and linearization. And well, in main part of the talk, I will just focus on this, which is kind of living on the discrete level, on the level of an algorithm for solution of a nasty system of nonlinear algebraic equation, discrete. But in the last part, I will also show you that, well, anyhow, whenever we already have an estimate for the discretization error, well, we can go one higher level and yeah, do adaptivity on the PDE side, and in a sense only stop when the overall error is reaching some specified tolerance. You guarantee the overall error. Well, I've included this picture to conclude the introduction. It's taken from a simulation that I will describe in details later, but hopefully this will give us a good feeling of the practicality of all of this. So I am using some numerical scheme to discretize a Richards equation. It's one-time step, so I need to solve one nasty system of nonlinear algebraic equations, and I do it with the approach I just described. I take some regularization parameter, well, it will be epsilon equal to 0, 1, which will give me this starting line. I apply just a simple pure Newton to a rather nice, non-problematic nonlinearity. Newton converges rather fast. And this few steps means here 4 steps. I stop them when I'm 3 times below the regularization error. And then I iterate. I take the regularization that was 0.1, I cut it, I make it smaller, I make it 0, 0, 1. I go to the next curve in this iterative regularization, in this sequence of curves approaching the nasty one. And I start the Newton from when I was before. Again, in few steps, I'm done. I am sufficiently below the regularization. Then I again go down with regularization parameter, again, start Newton from when I was before. In few steps, I'm done. And at the end of the story, I'm here. My linearization error is essentially 3 times below the regularization, and the regularization is essentially 3 times below the discretization. The discretization will always be there. Our posterior estimate of the discretization error, this red curve, from theory describes in the limit the true discretization error that is there. And my procedure ensured me that I've reached a sufficient precision. You see, anyhow, the discretization is not moving here. And I've reached it in some, I like it philosophically a way. I always do a few not too complicated steps that help me to move in some good direction. I don't try to be, not trying to make some huge, super complicated step. So that would be the procedure in a nutshell. Well, in the rest of the talk, I would like to give you details. I've chosen for this the specific case of the Richards equation. So all the details will come there. The specific form of the Richards equation I'm considering, the numerical discretization. We'll go back to the regularization, this sequence of nice functions approaching the nasty ones. I will describe linearization. I will give you details for Newton. I will also mention first order Picard type schemes. These 2 parts will be on really the heart of the story. What are these elements that allow me to steer my procedure? What are the a posteriori error estimates of the error components? And this will be now in specific numerical examples to see how does the procedure work. I will spend most of my time here. I will quickly then go to, in much more general problems, multiphase, multicompositional, but with phase transition, which means complementarity problems, inequalities, just to explain that the same approach applies there as well. And at the end of the day, I would like to go briefly to this last point that I'll be treating the discretization error. So I'll put all of it together, not just the adaptivity that I do here, but the fact that I can estimate also the discretization error, and I will show you how for rather complicated problems we can certify the overall error committed in numerical simulation. So this will be this last part here. Okay, so the Richards equation, I believe, is really a fundamental model for many things in porous media. It's a partial differential equation that models flow of water and air through the soil. We have it written here. I look for pressure P and the saturation S of P in my computational domain omega. While I'm a mathematician, for me, omega is a Lipschitz polygonal polyhedron or interval in 1D. I look for a solution on the time interval 0 to capital T. The physical parameters are the diffusion tensor K, are the gravity term G. Then I have the initial saturation prescribed, some source function prescribed, and mostly, or my focus goes to the presence of these two nonlinear R to R real-to-real functions S and kappa. You've seen them already. The S is the one which gives me the relationship between pressure and saturation, and the kappa is the one that gives me the relation between saturation and the relative permeability. I've shown you a while ago the plots for the Brooks-Corey, the red curves. Well, very much popular is the van Genuchten family, and there are many more. They are often of this form here, and again having this king here, so non-smooth, approaching 0 in terms of values or derivatives, so the degeneracy. Okay, so hopefully it's a known model for all of you. If not, it's evolutive nonlinear degenerate PDE that becomes something discrete whenever I apply a discretization. I've chosen a textbook one, backward Euler time stepping, lowest order continuous finite elements in space. But we may think of any other approach you like to go to the discrete level to obtain this line here, which represents a set of nonlinear algebraic equations that are nonlinear in a nasty way. They may be non-smooth, non-differentiable, non-degenerate, and degenerate. So PHN will be this piecewise affine and continuous numerical approximation of a pressure. S of PHN will be the approximation of the saturation. This is the one on the previous time step. And this capital F is a nonlinear function, which is essentially the composition of the kappa, the relative permeability function, with the pressure saturation curve. So F essentially is S composed with the kappa composed with S, and apply the gradient of Q. So this is a nonlinear system that is somehow in some form in all the computers that do numerical simulations of Richards. You may not have regularization, but regularization is again trivial in the way I'm describing. I don't take the black curve. I rather take one of these color curves, both for the nonlinear function S and the nonlinear function kappa. I index them by epsilon, more precisely epsilon j, because there will be a sequence of these parameters, and j bar will be a stopping parameter, stopping index for these parameters. So now this is still a nonlinear system of algebraic equations, but it's a nice one. It's differentiable, it's smooth, it will not blow up immediately your numerical linearization scheme. I will need in a few whiles this function f epsilon j, which is essentially nothing but a composition of this regularized kappa, regularized saturation, so composition of two smooth functions. Bear in mind, f epsilon j will be a nice guy. Finally, this is also in all of the codes doing numerics for this type of PDEs. Well, in order to get an approximation that you can touch, you introduce an iterative linearization. Well, there are details for two popular ones, Newton, with these choice for these variables L and psi, or Picard, modify Picard, first order here and then derivative here. Now this object here, F, indexed by time step n, mesh size h, regularization step j, and linearization step k, is a given function that is expressed here. It's kind of sitting already in your code. There's nothing to do with it than to take it and evaluate. And we will need the guy which is there in the code. Okay, so how do we proceed to make our strategy? First of all, we'll need the a posteriori estimate. The way we do, we take this object available in your code, lying in the heart of your numerical approach, something like minus gradient for Laplacian. which will be a field that will typically be discontinuous in terms of normal component along the edges. It will be a non-physical flux, non-physical Darcy velocity for your Richards flow. And we'll locally post-process it. From the green, from the blue, we'll go to the red. This procedure is called flux reconstruction. And we are using a very, very trivial one in this here. In a sense, anytime along the edge, I've got two directions that do not match, I just take a mean value. I make an object that is normal trace conforming, that is physical, that is H-diff conforming as I show it here. Okay, so that's the heart of it. This is available. It's local post-processing procedure, trivial one that I employ. And like this, I now have all that I need available to put in place this steering machinery. So what is my steering machinery? My steering machinery is given by these three computable a posteriori error estimates. If I start from the last one, it's an estimate that expresses how big is the error from regularization. It's essentially just taking the current pressure, plugging it into the original non-regularized function f, and comparing how big is the difference with the regularized one. Linearization, similar story. This is the nonlinear, or regularized but nonlinear function, and this is the linearization. So I just compare the two. The size of it gives me an estimate for the linearization error. If I try a regularization parameter to 0, this goes to 0. If my linearization converges, this goes to 0. Well, the last component is my discretization error. That's the a posteriori estimate known from the numeric side. And it's just comparison. Well, it's a difference of this blue and red curves. It's the original non-conservative flux compared to the conservative one. One thing I would like to stress is that these three quantities take the same form. There are some L2 norms of some piecewise discrete objects, piecewise polynomials maybe. They have the same physical units. They have units of fluxes. They compare always two fluxes, non-regularized with regularized one, linearized one with the nonlinear one, physically conforming and non-conforming one. And they speak about the same thing. They speak the same language. It's not the case that you measure the algebra by relative algebraic error, linearization by the difference of the two consecutive iterates, regularization by some regularization residual. Now, you make all of them speak the same language. And this is then why you can compare them. And this is the only thing that you need to insert or modify in your code if you already have one. Essentially, you just touch two lines in your code. The line, when do I stop my linearization? This is here. And this expression of the fact that I'm not bothered by the fact that I have a little bit of error from regularization the moment it is below the discretization one. Okay, so let me show you how all of this works in numerics. I have 4 test cases. I start from a rather academic one where I consider this van Genuchten model, and we can compute a lot of things in all details. I just re-show you again the simulation I'm showing you. So how does our procedure works in such a setting? For solving this nonlinear, non-smooth problem, I have this sequence of nicer problems with the regularization parameter going down. And all the time I just apply Newton. Newton converges rather fast in few iterations. I stop it when it's below current regularization, try the regularization down until it's below discretization. And this is where I stop. So let's go to something a little bit more interesting. It's what we call injection case. I now take the Brooks-Corey model, and let's compare the strategy we've now described in details, called the adaptive regularization with some given initial regularization parameter epsilon bar. Let's compare it to 3 rather common strategies used in practice. So first, but last in this list, just a pure Newton method. So I've got a rather nasty nonlinear system. I try to use Newton. Well, I see that even on the very first time step, I am not able to solve the nonlinear system. After 300 unsuccessful iterations, I just stop. Then there is a strategy of time step cutting. So very, very usual Newton method, but I employ the very classical strategy. Newton does not converge, cut the time step, everything is fine. You can prolong your time step back. So this is the screen curve. Well, we see that in function of time, we have a rather nice, limited, small number of Newton linearization iterations. But you may already spot here that there are many dots there. Yeah, the time step has been cut rather severely. And then there's this modified Picard. So lower order linearization scheme, which converges quite reliably all the time, but may have rather increased number of linearization iterations per each time step. So this information per time step is definitely not all, but that's what I plot cumulative. So I just sum the number of linearization iterations I need along my simulation. The simulation progresses. This is my physical time steps plotted. And I just plot how many iterations of linearization I've done in some weight from the initial time, from 0. So again, Newton does not converge at all. Well, there are just few iterations of time step cutting Newton, but if you sum them, it's a huge number of iterations. Picard is doing much better. Well, there are many iterations, but yeah, just one number per time step. And this is for me, very much natural strategy, always just move a little bit in the good direction. You see in this specific case, we have something like 10 times less overall iterative linearization iterations in the simulation with keeping the same method, just the Newton, not touching it. Okay, of course, you will ask me, do we lose a precision? Well, we have theoretical answers to it. In the limit, no, but you may be interested by picture. So here's it. The left one, it's a saturation field somewhere in the middle of the simulation, obtained with this method that applies adaptive regularization and Newton. And the right one, it's one of the standard numerical approaches, iterative linearization by modified Picard. Well, maybe you'll spot some super tiny details. I don't really know where, maybe somewhere here. But okay, eyeball measure, essentially non-distinguishable. Okay, the next one, we call it a realistic case. Again, you've got all the parameters here. It uses the Brooks-Corey model here. And it's a bit more realistic in that, yeah, there is a jumping diffusion coefficient, so some heterogeneous media, some inhomogeneous Dirichlet and Neumann boundary conditions, in some jumping discontinuous initial saturation, things like this. Let me again present these practical testimonies about the computational performance and cost. So again, as time goes on each time step, I plot the number of iterations that my linearization scheme needed. Newton does not converge the first step, 300, and I don't pursue it. Newton with time step cutting, always a small number of iterations, but many time steps. Modified Picard, potentially rather increased, sometimes a lot of iterations needed, but always make it. And the adaptive regularization and linearization strategy, just a few linearization steps per time step and no cutting of time step. If you wrap up, similar result as before. Well, the time step cutting may be better than first order Picard, but not really in the limit. And again, this strategy we've suggested seems to be pretty nicely working a couple of times faster than what you would have usual. This is the same type of plots I started with motivation. So again, it's a sequence of progressively more and more difficult problems, but always Newton converges nicely up to some exceptions. So that's what I want to show you here. It may happen that, yeah, the Newton stops to converge. Well, what do we do in such a case? Well, we've been on some epsilon parameter 0, 0, 1. We cut it to 10 times and it turned out to be too much. So we do some kind of, go back resolution strategy. We go back, but just cut the epsilon not 10 times, but just 3 times. So that's what's going on here. And then the Newton converges. So it's not touching the time step, but kind of touching the way how fast we regularize the nasty function. And this is what was beyond this simulation. The last one, we call it perch water table. Now finally with some physical dimensions, simulation of 1 day. Sand, clay, and again sand as usual materials with hopefully now bit reasonable physical properties. This is essentially what's going on. You have this infiltration from here and this barrier. And actually, in this case, of the 4 methods we've been testing, there was only one that could converge, where the iterative linearization converged, and it was this adaptive regularization strategy. It's a nasty case. Probably one should employ things like variable switching, and then the other methods would work as well. Well, we did not do it a bit on purpose. We wanted to show that, you may not need variable switching. This rather, brute force approach, always a small step, makes it at least over this case. So I would like to now switch to a much richer class of things. It's a short section, but of course, very much important for many simulations in porous media. So structurally, in many problems, you have complementarity constraints, you have phase appearance and disappearance, phase transitions, which mathematically leads not only to equalities, so algebraic equalities, systems of algebraic equations that are nonlinear, but as described here in the second line, you obtain inequalities, or more precisely in this writing, complementarity constraints. Then usually one employs a completely different methodology to numerically treat this. And my point is to show you that, you may do it, but of course, you're not forced to it, and may use the approach I just described essentially in the same way as before. The first step is that, well, this is well known, these type of complementarity problems, which are written as algebraic inequalities, can equivalently be written as algebraic equalities. Well, you keep this first set of equations untouched, nonlinear algebraic equations, and you change the complementarity constraints into, which had inequalities, into again equality. You use for this purpose complementarity functions. And the price to pay is that even if this part of your nonlinear algebraic system had functions that were not nasty, that were smooth, were differentiable, and maybe non-degenerate, now from this part, you will definitely have non-smooth nonlinearities, different nonlinearities that you cannot differentiate. So in a sense, you are now immediately in the world that we've been interested so far, systems of potentially nasty systems of algebraic equalities, nasty in a sense that the nonlinear functions are non-smooth and non-degenerate. Well, how do these typical C complementarity functions look like? What is in the heart of them? I'm drawing you 2 examples. I'm showing you the absolute value function that is behind the semismooth Newton approach, where the complementarity function is a Newton min one. And I'm showing you in black curve the Fischer-Burmeister function, another popular C complementarity function that allows you to change, once again, a system of inequalities into an equivalent system of equalities. And we just see that both of these black curves are R to R functions that are non-smooth, that have no derivative here in this point or here in this point, but where you can immediately feel, well, you can approach progressively these nasty black functions by these nice red ones. So that's exactly what we are pursuing as approach. We regularize iteratively or adaptively, and we are completely in the box that I've been describing so far. So let me just show you three more precisely computational results. Yeah, I picked some of the numerical simulations from this paper, so all the details can be found there. Apologies, I don't give you all the specification here. Structurally, I want to focus on how different numerical methods, different iterative linearization schemes behave in terms of number of their iterations, plotted with respect to either number of mesh elements or when I plot the CPU time of these methods with respect to the number of mesh elements. So what are the different methods? Well, this is the out of the book semismooth Newton with the Newton min function. Well, it converges, it reaches the goal, solving the system of variation inequalities, but you see you pay a rather increased number of iterations and you pay a rather increased CPU time. At least in the test case I'm presenting, the Fischer-Burmeister is doing much better. And then the methodology available, specific one, I'm just picking one. It's called path finding strategy. So semi-smooth Newton type methods with path finding. It does very nicely, both in terms of number of iterations in function of mesh elements and CPU time in function of mesh elements. The last two are essentially out of the box of this approach. You don't need to implement anything specific in your code. You just go with Newton, that's it. And you see, yeah, they are, I would say, at about as a dedicated function. So my personal point is that, yeah, it might be that with simple adaptive regularization approach, you have the possibility to go with very simple, just Newton and obtain things that work as well as a dedicated method. So one little example, these are then the details which are behind this adaptive regularization linearization. So again, different components and you move them little, always just a few steps and then stop. And yeah, this was another test case. Now comparing the adaptive approaches. So one is A in the black curve and this one in time and number of iterations against yet another class of methods, the interior point methods. So again, dedicated methods like interior point, you may have similar performance out of very simple procedure, just replace the non-smooth function by a sequence of regularized ones. So I made it to the last part of my talk. So essentially these first two ones were about the title, adaptive regularization and adaptive linearization. And here I would like to give you a little bit of outlook, saying that with what you already put into your code with these two parts, you're immediately in reach of this third one. You can also certify the overall error in your numerical simulation. Because maybe let me go back. You've seen we already have in our adaptive regularization and linearization, we already have in the code this a posteriori error estimate of the error committed by a numerical scheme with respect to the PDE. So this is what I would like to give you some more details on in this last part. So I'm taking it in the Richards equation. So we've seen this, absolutely the same notation as in the first part of the talk. Again, with these problematic functions, and you can go all of these adaptive regularization strategies to produce some numerical approximation. Now, when I have the numerical approximation, I would like to give you the details. How is the error? How big is the error in it? For it, it's a little bit of math. I need some good function spaces appropriate to the setting of the Regularization equation. For the theoretical study, not for numerics, I need the Kirchhoff transform. This is a notion of a weak solution, which gives rise to the notion of the residual of the partial differential equation and of this size, dual norm of the residual. And then the theoretical work will be relating the size of the residual with some notion of error. It turns out appropriate to use these time integrated things where you fight the appearance of exponential to the final t of the usual Gronwall lemma. So these are time integrated L2 norms that are equivalent to L2 norms, but have much better equivalence constant than exponential to the final t. That would be a short description of what is it. And then with the help of these J time integrated functionals, this is the link between the error in saturation or in pressure to the residual, more precisely, the dual norm of the residual. Essentially, the error in some norms is below the norm of the residual, and similarly here. Once we have it, we can bound the residual size, the dual norm of the residual, by computable a posteriori estimate, and just wrapping up some time of L2 integrated norm, so this is the full detail, is at the end of the day less than or equal to a fully computable number, a posteriori estimate for the L2 error, some kind of H1 integrated norm, less than or equal to fully computable number, your computable a posteriori estimate for H time error. So that's what comes out of the theoretical study. And in a sense, we already have in the code the components of this L2 and H1 estimator. So let's now test this, focusing on this overall error. Again, 3 test cases. First, an academic one with known exact solutions such that I can compute the exact error. This is how does the test look like. It's a degenerate region where the saturation becomes 1, does not go over. We have an estimator for this error coming from the degeneracy, which is this red one. You see, when it's an evolutive problem, when the saturation hits the 1, yeah, that guy gets in. And showing the overall result, the methodology allows you indeed to estimate the question, how large is the error in a numerical simulation of something like this? We have these a posteriori estimators computed along the simulation. This L are different discretization levels, coarse, finer, and finest. Here we refine the mesh and time step, the error goes down. L2 integrated, H1 integrated. So this is what we always have. These are a posteriori estimates computed. Test case, we also have the errors, the L2 and the H1. So we can plot the ratio, estimate over error, answering the question, how many times do I overestimate the overall error in my simulation? And you see, even for a rather nasty problem like this, degenerate, time dependent, the overestimation factor is something like 5 for the L2 norm and 4 for the H1 norm, which I personally think it's pretty good. Most importantly, it is constant. So you see the evolution of the errors may be definitely non-constant with respect to time. The estimators evolve in the same way as the errors, which means that the ratio, the effectivity index, is constant along the time. And this is what we call robustness with respect to the final time. Well, let me pick the second one. We call it realistic. We've already seen this one before. This is it. We have per time step and per mesh element a number. This is the component of the a posteriori estimator. That is what is plotted here. And actually, not only we have one number, overall error, we have this information about the localization of the error in space and in time. So this is what I predict. And again, I can compare what is the reality. In the eyeball measure, you can see that we can predict very well, not only the size, overall size of the error, but also where the error is localized. Last test case, well, call it benchmark, Van Genuchten type saturations and relative permeabilities. This is the setting. Again, indeed a degenerate case with degenerate regions, rather hard one. If you look on the distribution somewhere in the middle of the simulation, element-wise of the error, this is log scale. They are something like 6 orders of magnitude. Somewhere the error is huge, somewhere the error is super small. Once again, that's the reality. This is what the a posteriori error estimate predicts. So it matches perfectly in the eyeball measure, and these are the things we can prove in theory. And also, if you take a look at the total error in the simulation, we again overestimated by a factor very, very close to 1. So that was just saying that the components we've been using in these first 2 steps are ready there to give you also overall error certification. So I'm almost done. Let me just conclude. I wanted to speak about adaptive regularization. So approaching nasty state laws by a sequence of nice ones, which in particular allows you to keep your favorite linearization scheme completely intact. If it's Newton, you just stick to Newton. You do everything with Newton. Don't need to change. It allows you to avoid timestep cutting, dumping, scheme switching, or even variable switching. The methodology is, of course, super old, supernatural. The thing that we are employing, how to steer it properly by our posterior estimates, where in particular we estimate the different components of the error: linearization, regularization, discretization, and also overall. So kind of as an additional benefit, we can certify the overall error committed in the numerical simulation. And I've been showing you a bunch of numerical results from different porous media flows, and I do believe that I could describe it as very sound numerical performance. All of what I've been presenting, and of course much more, can be found in these publications and preprints. And with this, I would like to thank you very much for your attention.
Thank you, Martin. Very interesting. And it's time open for question. You can just unmute your microphone and talk if you prefer, or you can use the question and answer tab in the Zoom and write down your question if you have any. So I think there are quite a few participants. So
I think participants need to raise hand, and then we can allow them to talk. So
okay,
if you have questions.
Yeah, yes, otherwise it's... Yeah, Sorin. Oh yeah, I need to allow you to talk.
Thanks a lot, first of all, to Martin for the great talk, and also to the organizers for inviting Martin for such an interesting talk. I have one question about a topic you addressed in the beginning, which is basically changing the regularization parameter. So from a theoretical point of view, because practically it seems to work, clearly, but from a theoretical point of view, are there any rigorous results guaranteeing that the solution you get after a number of Newton steps for one regularization parameter would be a good initial guess for the solution with a smaller regularization parameter?
Okay, thank you, Soren, for a picky question. You're completely right. So let me try to answer it in 2 or 3 levels. So first of all, we did rigorous mathematical studies, but admittedly not for the Richards equation. We took some easier test cases with non-smooth and degenerate functions, and then we could prove things. So then answers would be affirmative. If you iterate enough your linearization, then you reach a good guess for the next step. And in the limit of both linearization and regularization, you hit the solution that you look for. So there is this first paper with François Ferrot and Ari Rappaport having these type of results in it. We, as I said, did not do anything like this in the Richards equation setting and beyond. on the other hand, we do have rigorous results in these settings as well for the overall error. So at least we can say whenever you do such a procedure, what you obtain is guaranteed to be to a number that is given to you in the distance of the true solution. Okay, so in that sense, even if something goes wrong, at least you know that it went wrong for whatever kind of complicated problem. So that would be my two-step answer.
Thank you very much. Thanks.
I have a question again on the regularization. I suppose there are many ways you can regularize a function. Is there a better way? I mean, are there some properties that you want to this series of regularization to have?
Yeah, thank you, Luca. Again, very good question. Okay, you're grilling me. So in the results I've mentioned, rigorous ones we could have, essentially all we needed is this sequence of the color regularized functions converges pointwise to your given nasty function, and then some properties of the target one and the sequence. For instance, if you study problems that are monotonous and Lipschitz continuous, then the target one for the problem to be well posed, but also all the individual ones that approach need to have a uniform bound, say, on monotonicity and Lipschitz continuity. Other than this, you don't need anything specific. Of course, you're completely right. In practice, there's a tons of way how to do things. Maybe the two big classes are either you take this epsilon, you go epsilon to the left, epsilon to the right, you don't modify nothing here and nothing there, and use some kind of polynomial approximation, which would be called local regularization, or you just do something at the scale of the whole interval, which I would call global regularization. And then practically, we've tried both were working. And once again, they are not impeded by the theory we could do for some specific cases, both would work. Yeah. That's what I would say.
Thank you. Any other questions from the participants? Another one from Sorry. I think you're still allowed to talk.
Thank you. So if I'm allowed to tease Martin, yeah. So also about the convergence behavior, we saw that basically if Newton is converging, then the error is reduced very rapid. It's quadratical. So in some sense, it's doing a lot of work, too much work, because then the other errors are dominating. So I'm wondering, because on the other hand, Newton is quite expensive in time and also not guaranteed. So I'm wondering if you use, is it an option to use a simpler maybe, but maybe not that fast scheme, but still where you know that you converge, but you don't reduce that much the error, but you're happy, you reach the level you want to obtain. Yeah. Is there any option in this way?
Yeah. So all I've presented, all the numerics we did, all the pieces of rigorous theory that are there for more toy problems, absolutely no importance of what is your linearization. It can be whatever. The approach is about how do you branch pieces together, but each of the pieces can be what you wish. So typically I speak about Newton because yeah, for me, it's one of the first choices, and I like to be able to use it also in nasty situations. But once again, in all of I've been presenting, it can be whatever scheme you pick it. And kind of the point I like about the approach, you can stick to this one favorite linearization scheme that you have, and you don't need to think about changing it or adjusting it in different situations. You can go along with the one you have all the time. You kind of don't touch the way how you attack a nonlinear problem. You rather adjust the nature, the strength, the stiffness of the nonlinear problem. And then for nonlinear problem, when it comes to it, you go with your method. So it can be whatever method. Well, we use Newton. You're completely right. It goes very fast down. It's seen in, for instance, this picture here. But you see, we don't. That's kind of the point of the whole methodology. It goes super fast, but when it's sufficiently small, we just stop it. So we need 2-3 iterations of it and not more. If we would use some slower first order method, probably the green curve here would be much less fast going down, and you would need more iterations. Yeah, you're right. You may not have. Yeah, you may avoid assembling Jacobian, stuff like this, where the Newton is expensive. Yeah, you may think about frozen Jacobian. But again, all of this enters perfectly the framework. Okay, the point is essentially have your scheme as it is in the code. Anyhow, if you have a iterative linearization and maybe also some regularization in the code, you have somewhere in the code these two lines. When do you stop the linearization and how do you adjust the regularization? And my okay, the experience I would like to share is that it's, from my viewpoint, super important that these stopping criteria don't speak about two consecutive iterates or residuals or incompatible things that kind of go in the philosophy with the same target object, some energy norm, some L2 norm of the Darcy velocities, and that the things are expressed in this way. And whether the regularization f epsilon j here is this or that, and how this linearization has been obtained, just like in my example here, was it obtained with modified Picard, with Newton, or with something else? That's completely irrelevant for the methodology. The methodology is about how do I construct the estimators, and that I should evaluate this as my estimate for the size of the error components.
We have one more short question. Aisha, would you like to unmute yourself and ask? If
Yeah,
not,
okay. Thank you, Martin, for such a nice talk. I'm just curious about what criteria are used for decreasing epsilon during the iteration. I think it's linked to the first question of the story.
Yeah, thank you. So very much practical question, and in a sense, we were yeah, we started to do things super simple and we never moved out of it. So we start with epsilon being 0.1, then we go to 0, 0, 1. We always divide by 10, and that's it. It may happen, and this is the picture here. Once again, it may happen that with such a rather naive, direct, non-defined, but also simple thing, just divide always by 10. It may happen that you bring your linearization, in our case, Newton, to difficulty. So this is this thing here. It stops to converge. And then we just did again, some procedure to capture things. So we conclude this is too big step of regularization, going from 0, 0, 1 to 0, 0, 1. Well, so let's just kind of go back and try once again, but with small gap. So from 0, 0, 1, 0, 0, 3. Whatever kind of how to say, practical recipe would probably work there. And of course, there are no proofs at this level. This becomes very much engineering practical, okay? You have a strategy just like the time step cutting or whatever. But it's reasonable in that, okay, you try to go always little step by little step. If it does not work, you can always just get the last point where you're fine, and try with a step that is not that big, because the big steps may be difficult.